All right, everybody. We're going to go ahead and get started. Everybody's quizzes from last weekend should be graded. Hey, Brooklyn. And I'm most of the way done with polyatomic ions quizzes. So you should see grades start showing up if you're at the beginning of the alphabet. Then you should have a score there pretty soon. If you still haven't taken that quiz, let's do that by the end of the day today if possible. So talk to me, unless you've already talked to me about it. So you guys are asking really good relevant questions that I'm going to go through a bunch of, but there's a few random questions that we're going to talk about a bit. I'm actually going to talk about diamonds and graphite more later when we talk about phase changes. But it's a pretty common question. I get this question every time I teach this class. Somebody asks about diamonds versus graphite. They're both pure carbon. So what's different about them? Their Lewis dot structure and their molecular geometries. Carbon is a bunch of diamond is a bunch of tetrahedral carbons that are all linked together in this three-dimensional lattice structure. So it looks like you doesn't want to give me my marker today.
It popped up on the last one.
Oh, that's what it is. It's down here. We go. So a diamond is a tetrahedral carbon that's linked to an almost infinite number of other tetrahedral carbons. I say almost infinite because we're talking about moles of atoms here. And so it's not actually infinite, but when we talk about something that's like 10 to the 20th atoms, we can essentially treat it like it's infinite when it comes to visualizing this. So every single one of these carbons is tetrahedral and attached to 4 other tetrahedral carbons. So you get this three-dimensional structure where every atom is attached to every other atom through connections, and that gives you an overall shape. Let's see if they have this one in my favorite crystal structure. Yeah, they do. So you get something that looks like this. Every single one of these black circles is a carbon that's tetrahedral, and so it's attached to 4 other tetrahedral carbons. And so if you look at these, you get this really, really strong structure, and you can drag it around and look at it. You can see why diamonds have a reputation for being so hard, because there are so many bonds holding the entire thing together. If we compare that to graphite is still just carbon, but it's a bunch of trigonal planar carbons that are all linked together. There we go. Where we have alternating double bonds, and every single one of these hexagons is connected to 6 other hexagons. So we get a bunch of flat. That doesn't work. I put the double bonds in the wrong spot to show this properly. But basically you wind up with these big sheets of carbons that are all flat because all the carbons are trigonal planar instead. That changes the electrical properties and the physical properties because those sheets are all pretty strong, but they're not connected to each other very well. So it's a little bit like if you rub graphite on a surface, it's a little bit like taking a ream of paper and doing this off the top. Every sheet is attached to itself, but they're not attached to each other. Right, and so that's why we can use graphite as we call it pencil lead, because when they first discovered graphite, they didn't realize that it was carbon. They just said, well, it looks kind of like lead, so we'll call it lead. They thought they discovered a new type of lead at first. But basically what you're doing when you're writing with a pencil is you're just rubbing off layers of graphite and they leaves behind a sheet of graphite on your paper when you do that. It also means that the electrical properties are different because these alternating double bonds are a way to move electrons around. But tetrahedral carbons can't do that. So diamonds are not conductive, but graphite is. And so it all comes back to the electrons and these Vesper geometries. When we start talking about this, we call this the study of solids and liquids. We call it condensed phase physics or condensed phase chemistry, or material science. Because most of the time when we first introduce chemistry, we're mostly talking about gases because it's a lot easier to think of these as being these isolated systems in space. But if we want to start talking about solids and liquids, more complicated stuff starts happening. So in Gen Chem, we'll spend some time on crystal structures of different compounds and different materials and start looking at what something like those lattice structures look like.
What was that website?
Chem2 3D. It's run out of, I think it's the University of Liverpool, Waterloo,
Right.
Some British university.
Yeah, that's cool.
Yeah, they have a lot of good, good 3D animations. All right, and then somebody asked about how do we get all these new elements on the periodic table? Basically, that's what a particle accelerator is for. The way we make new elements is through fusion reactions. And the way we get fusion reactions to happen, if we don't need them to be self-sustaining or as a power source, literally all we do is we take pieces of stuff and we accelerate it really, really fast using a particle accelerator, then we slam them together. And if we have the right combination of nuclei and at the right speed, when they slam together, the nuclei stick together and make a new nucleus. And if that happens to have a new number of protons, you just made a new element. So these days, most new elements are not found by going out and digging through minerals or anything like that, like they used to be. Now we're finding new elements. We only find them basically in particle accelerators because we've gotten to the point where all of the new elements we're discovering would require more energy per atom than a supernova. So they don't occur naturally anywhere in the universe that we're aware of, but we can make them ourselves with a particle accelerator because we can put more energy into really small systems that way. And that's why if you'll notice on the periodic table, a lot of them, the newer elements, the F block elements in the bottom row of the D block, are named after places in California. That's because a lot of those ones were discovered at the particle accelerator in Palo Alto. They had a smaller one in Berkeley, where they had one in Palo Alto. So Berkeley was discovered a particle accelerator in Berkeley, et cetera. Most of the ones discovered in the US were discovered in California, with the exception of Tennessee, which was discovered in Tennessee. Oak Ridge, which was one of the satellite locations for the Manhattan Project, where they refined plutonium and uranium to make the atomic bombs at the end of World War II. Most of the refining was done in Berkeley and in Oak Ridge, Tennessee. Then they shipped the uranium or the plutonium to New Mexico, where they actually assembled the devices. How do electrons actually know where to go in an atom? Basically, electrons, and I know that they put "no" in quotes. I know that they're not anthropomorphizing too much, but they don't know anything. Everything that happens in the physical universe is happening because matter is becoming more stable in one way or another. In the case of electrons and the shapes of those orbitals, that's happening because those electrons are attracted to the nucleus, because what's the charge on an electron? Negative, and charge on the nucleus is neutral when you've got enough electrons around it, but the nucleus itself is positive, right? So electrons are being pulled towards the nucleus, but they can't fall all the way to the nucleus because of the Heisenberg uncertainty principle. Remember, the Heisenberg uncertainty principle says that you can't know both where something is and how fast it's going at the same time. So if you actually let an electron fall all the way to the nucleus itself, it would be stuck in one tiny little spot, and you would know both where it was and how fast it was moving because of the temperature. Since you can't know both of those things, electrons are not physically allowed to make it to the nucleus. They're trying to get to the nucleus, but they're stuck at these energy levels because they can't actually fall all the way to the nucleus itself. And so Heisenberg uncertainty principle is really, really weird that way. It's really counterintuitive, but it's basically just a function of how the universe works. That you can think of quantum mechanics, the rules of quantum mechanics is basically the boundary conditions where you're basically say, okay, well, there are these set of rules that govern how matter behaves. Quantum mechanics is the set of rules that governs how matter behaves when things are really, really small. And so it's not one of the fundamental forces that causes the shapes of the orbitals. It's basically the limits of how much we can know about a particle at any given time. All right, these are all the ones that are more relevant. So, and some of these are similar to each other. So I'm not going to spend a ton of time on all of them. How do the strength of different types of bonds change? What is it about ionic bonds versus covalent bonds? Why are they different? And what's their relative strength? Well, covalent bonds in general are weaker than ionic bonds because a covalent bond it happens when you don't have enough electrons to go around for all your nonmetals. Because nonmetals are trying to gain electrons and metals are trying to give away electrons. So covalent bonds overall are weaker than ionic bonds because ionic bonds, you get a full-on positive charge and a full-on negative charge stuck together like a magnet on a fridge. But the difference is that what happens when you add water is you add a whole bunch of small interactions. When we actually put sodium chloride in water, you don't actually get sodium chloride anymore. You get sodium ions that are surrounded by water molecules. Because these water molecules have a partial positive on them. Because they're what type of molecule? What type of molecule has partial positives and partial negatives? Polar. It's a polar molecule. I realize I phrased that question kind of awkwardly, so sorry. They're polar molecules, so you have this partial negative on a water molecule. That partial negative is attracted to a sodium ion because sodium ions are positive. So basically, when you take sodium chloride and you dissolve it in water, you're replacing a single ionic bond that looked like this, where you get a positive ion attached to a negative ion. You're replacing one of those with about 6 partial bonds. Because all of these water molecules wind up aligning around the sodium. And then the same thing happens with the chloride, right? Because chloride's a negative charge. You wind up with chloride being surrounded by the hydrogen side of a water molecule. Because that's a partial positive. So even though ionic bonds are stronger than covalent bonds, we can still pull them apart when we dissolve ionic compounds in water because we're replacing one strong ionic bond with 6 pretty strong bonds. These attractive forces are not as strong as a covalent bond or nearly as strong as an ionic bond, but you get a whole bunch of them when you dissolve it in water. So all of these forces that are holding these molecules together, holding these solids together, are all based around how do I maximize the attractive forces? How do I get things to be as stable as possible? And the way that ionic compounds behave when you dissolve them in water is they split up so that you can surround each of your ions with a bunch of water molecules. And that overall, for some things, is more stable. Not all ionic compounds dissolve in water. Most minerals are ionic compounds. I guess I can't say that. A lot of minerals are ionic compounds, but they don't necessarily dissolve in water because they have stronger ionic bonds than sodium chloride. So we'll talk about how reactions happen and how minerals form when we have opposite charges next to each other, and we'll find out that not everything dissolves in water. In covalent compounds, when we dissolve in water, they don't break apart at all. Because if you did that, you would actually have to break apart a molecule where everything has a full valence. It's already pretty stable. And you don't get nearly as many positive attractions, or I shouldn't use the term positive. You don't get as many favorable attractions when you break apart a covalent molecule. Somebody asked about metalloids. Two people asked about metalloids. How do we know if it's going to be ionic or covalent when we're talking about metalloids? You might notice on the version of the periodic table that I'm going to give you on your test, the metalloids aren't marked, but that stair-step line between the metals and the nonmetals is. For this class, we're not going to really split hairs about metalloids. It's either a metal or a nonmetal. And so anything to the left of that stair-step line is a metal, anything to the right of that stair-step line is a nonmetal. So don't get bogged down in this. But if you do want a better answer as how do you know if it's ionic or covalent, if it's a metalloid, basically you look at electronegativity. Remember that when we looked at whether something was a polar bond, we also had a list of, or had sort of a threshold for difference in electronegativity. If it was between zero, if our difference in electronegativity was between 0 and 0.4, we said it was non-polar covalent bond. And if it was between 0.4 and either 1.8 or 2, depending on what textbook you grab, we called it a polar covalent bond. And if it was greater than 1.8, we called it an ionic bond. So if you want to know if your metalloid is going to make a covalent bond with a nonmetal or if it's going to make an ionic bond, you look at their electronegativities. Turns out that there's actually several metals that can make covalent bonds with carbon, for instance. Because carbon is pretty low electronegativity for a nonmetal. And so if you pick a metal that has a higher electronegativity for a metal, they're close enough you can actually get a covalent bond. That's the sort of thing we talk about in organic chemistry, not necessarily the thing I expect you to know for this class. So for this class, we're just going to use that stair-step line. We're going to ignore the fact that metalloids exist. Everything's either a metal or a non-metal for the sake of this class. I like that you're asking questions about that and that you're aware that there's some gray area, that it is a spectrum for how these types of compounds form. But I'm not going to test you on that for now. Come back for Gen Chem if you want more details. Chemistry has a reputation of being really frustrating to study because every time you take a chemistry class, we tell you that what you learned last year was pretty good, but not good enough. So basically you unlearn what you learned. When you take Gen Chem next year, you're going to unlearn some of the stuff I'm teaching you now because we're going to really dive in and start splitting hairs more. And then the year after that, when you take organic chemistry, we go further down the rabbit hole until we don't have to do that anymore. And then we're just really doing theoretical physics, but it all connects eventually. So all three of these, I think I addressed. How do I know what category compound belongs to? If it seems like it could belong more than one, just if it's metal and a non-metal, it's ionic. If it's a cation and an anion, like ammonium nitrate that was on the quiz, we're going to still treat it like ionic, even though there's no metals, because we still have something with a positive charge. And last but not least, just so you don't make any false connections here, can I assume every aqueous solution is an acid because all the acids so far are aqueous? No. It's a good question. All acids are aqueous solutions, but not all aqueous solutions are acids. So it's a bit of a Venn diagram situation. Acids are a subset of aqueous solutions. I want to put it in mathematical terms. All right, questions on any of this stuff? Like I said, these were all really good, relevant questions, which is why we took the time to go through them all in detail. So keep asking good, relevant questions. Let's do some practice with energy. If you were in lab on Monday, this is going to look really familiar because this is exactly what we did in lab on Monday, or what we're doing in lab today or tomorrow. Except we didn't know what our metal was in case lab, but basically all we did is we heated a piece of metal up, or several pieces of metal up, to a high temperature, and then we dropped it in water that was room temperature. If the final temperature of the water is 24.9 Celsius, how much energy was absorbed by the water? So just a reminder where we left off the other day. Heat, aka energy that changed hands, is equal to the mass of the object that's changing temperature times the specific heat, Cp, of the object times the change in temperature. So for this first one, we need to know, if we want to know what Q is for the water, we have to know what Cp is for water. Luckily for us, specific heat of water is always the same. Cp for water is always 4.184 joules per gram degree Celsius. If you want to change the temperature of 1 gram of water, you have to put 4.184 joules of energy into it for every degree Celsius that you want it to change. So for the water, we're asking about how much energy is absorbed by the water. So we want Q for the water, we need mass of water, Cp of water, which we know, and delta T for the water. So I know that that's intimidating to look at if you're not used to looking at scientific equations. Remember that these subscripts are just helping us keep track. We don't want to mix up the change in temperature of water with change in temperature of the metal. So I'm saying delta T of water, specifically, mass of water. All right, I'll give you a few minutes. Plug stuff in and get an answer. What's the change in temperature for the water? So we want to make sure we keep track of the signs properly, right? So delta change always means final minus initial. So if we wanted to actually plug it in, we could just type, write it in as final temperature minus initial temperature. Or you can do the math, you can do that subtraction before you plug it in and get 3.4 degrees Celsius. So plugging that into your calculator should be pretty straightforward, right? Not even dealing with any scientific notation or anything. What's gonna happen with the units? There's a bunch of stuff's gonna cancel out, right? We've got grams on top and grams on bottom, so grams cancels out. Got degrees Celsius on top and degrees Celsius on bottom, so those cancel out. So it's just joules, which makes sense. Joules is an energy unit, right? And I started this by reminding you that Q is the amount of energy that changes hands. So Q should be in an energy unit. If you use a different value, you can actually look up specific heat of water in a whole bunch of different units. You can go to Wikipedia, it has an entire page dedicated to specific heat of water. And just has a giant table of specific heat of water in different units. You can get it in calories per gram per degree Celsius. You can get it in BTUs per pound per degree Fahrenheit, and everything in between. This is the version that we're used to using. So because we work in joules mostly when we're dealing with energy in this class. But any energy unit has its own specific heat of water. And every substance is going to have its own specific heat. So what do we get for our final answer here?
7.8 times 10 to the 7.
So 780, we needed scientific notations, scientific notation, because we only get to keep 2 sig figs after we do that subtraction. So that's Q for the water. That's the amount of energy that went into the water. And we know that because we measured our temperature of the water before and after. And we measured the mass of the water. As long as you know those 2 things, you can figure out the number for the joules. Right? Questions on that first part? Not too bad, right? We also know that the metal was changing temperature as well. If the metal is changing temperature and we have a mass of metal, we could also figure out how much energy changed hands from metal. The water warmed up. Why did the water warm up? Where did that energy come from to warm the water up? From the metal. So this, again, this is review for those of you who are in lab on Monday. What does that mean we can say about Q for the water versus Q for the metal?
It's the inverse.
It's been a long time since I took a math class, but I'm gonna say it's the negative.
Yep.
Inverse, I think inverse means 1 over.
Does it? Oh.
Or is that? No, that's the reciprocal. Maybe inverse.
Maybe I'm wrong.
Inverse could work. Either way, the negative. We can say that whatever energy went into the water came from the metal. It does get this negative sign in there because what was gained by the water, it's a positive energy gain for the water, but metal had to lose that much energy. So that means if we know Q for the water, we also know Q for the metal. We're making the assumption that no energy is lost to the surroundings. That our container didn't absorb any joules of energy, that we didn't lose any energy to the heating up the air or anything like that. That's a decent assumption usually if we're careful about how we measure these things. How were the percent errors the other day for Monday's lab? Anybody who's done Monday's the calculations so far?
It was 7.7%.
Single digit percent error in chemistry is actually pretty good. Physics, they're a lot more picky because they're dealing with larger objects. They can actually get a lot more precision in their measurements because they're dealing with larger objects. Chemistry, it's a little bit trickier. So anything single digit percent error is pretty good. And basically for this lab, for how rudimentary our setup was, anything that's less than about 30% error is not half bad. If we practiced more and made some corrections, we can get that number down, but the whole point of this lab is just practice using this equation and this assumption. So that means we can say Q for the metal, for the iron, is negative 7.8 times 10 to the 2 joules. If we want to find the specific heat of the metal, we now have 3 of the 4 pieces for that Q equation, right? So we can say Q for the iron is equal to the mass of iron, Cp of iron, delta T of iron. And once again, we know all of those pieces except for Cp. So that's what we're solving for in this case. It's not super tricky algebra. This step here was really the biggest leap. Because then we can just plug everything in. Negative 7.8, 10 to the 2 joules equals 23.020 grams Cp. And delta T, I didn't leave myself enough room. Delta T for the metal, there's our initial temperature of the metal, and our final temperature is 24.9. So it's a much larger change in energy. Something just under 70, right?
Negative 66.
Feels like there's an Iron Maiden song in there somewhere. So now what we're trying to do is solve for Cp. Divide both sides by the mass, divide both sides by negative 66.6. And we get specific heat of iron. Should be somewhere around 1. No. 0.1.
Yeah, I have 0.51, but.
No, that sounds right. I'm just guessing. I looked at this and said that's about half as much water. And that's about 20 times the change in energy. And so I just tried to estimate it based on specific heat of water. But doing that mentally is not always advisable when you have a calculator in front of you. 0.51 you said?
Yeah.
We're back in joules per gram per degree Celsius again. Because we took joules, we divided by grams, we divided by Celsius. Also a reminder, I think there were 1 or 2 groups on Monday who left before I told you, before you found out what your metal was. So if you didn't get the actual identity of the metal before you left on Monday. Come by lab day and double check what metal you had, and I'll tell you what metal it was, and that way you can do your percent error. All right, questions on this Q equation? We are gonna keep using this, and we're gonna use this a lot today when we're talking about phase change. Because phase change happens a lot at specific temperatures, but you have to get your substance to that temperature before it'll freeze or before it'll evaporate. So the energy required to change the temperature of a glass of water, for instance, is we're gonna use the same equation. Anytime there's a change in temperature, we're using this equation. And for those of you going into engineering, this is basically the simplified version that looks at it as though everything is going to be constant at all the different temperatures. This subscript P here on the specific heat means at a constant pressure. If you have seen something where the pressure is changing, you actually get this weird differential equation. Or if you're starting to look at how fast energy is changing hands, that's actually different. This tells you the total amount of energy. But if you start involving the rate of energy transfer, you start getting into what's called Fourier's law, which is looking at what a temperature gradient looks like within a substance and how fast energy changes, but you need partial differentials for that. So you can't actually solve those until you've taken differential equations. So we just use a simplified version here because you don't have to have taken DiffyQ before you take this class. All right, let's talk about phase change. Everybody has experience with phase change, right? Especially us living up here in the mountains. We dealt with the interesting phase change just yesterday where we went from having all this snow on the ground to now being flooded with liquid water instead of solid water. Right, so we're used to thinking about phase change. The most common phase change that we deal with as humans living on Earth is water's phase changes. So we're going to use that as our sort of sample system for the most part. But a lot of the same ideas apply. And so just some vocab. When something goes from a liquid to a gas, we can call that evaporation. We can call it vaporization. We can call it boiling. All mean the same thing. Boiling is the phase change that happens when a liquid goes to a gas. The most common scientific term for it is vaporization. Means the same thing though. The opposite of vaporization, any of these phase changes that can happen in both directions. If you can go from a liquid to a gas, you can go from a gas to a liquid, which is commonly called condensation. Sometimes you see, we'll stick with condensation as our terminology there. Liquid can also go the other way. If you take even more energy away from a liquid, if you go from a gas and you take energy away from it, you go to a liquid. If you take even more energy away from a liquid, you go to a solid, which if we're talking about water, we call that freezing. If you're in the planetary sciences, or if you go into astronomy, they refer to everything that turns into a solid, they call it freezing. Going from liquid iron to solid iron is called freezing. In chemistry, we'll also use the term fusion. But that gets confusing because that's not the same as nuclear fusion. This is phase change fusion. So when we see numbers like this in chemistry, we're talking about not the nuclear reaction. And then we got the opposite, going from a solid to a liquid, we call that melting. It's the same for everything, right? We don't really have different terms for, I don't know, say butter. We don't usually refer to melted butter as freezing when it turns back to being a solid. But technically that's what's happening, right? But we use melting anytime we go from a solid to a liquid. There's one more type of phase change that can happen though. You can actually go, based on the conditions, you can go straight from a solid to a gas. Which seems counterintuitive because we're used to dealing with water. And at atmospheric pressure, water goes through a liquid phase before you can get to steam. You can't go straight from ice to steam at atmospheric pressure at sea level. But there are other things that do. Anybody know what dry ice is?
Solid carbon.
It's solid carbon dioxide. So carbon dioxide as a solid doesn't go to liquid CO2. It goes straight to CO2 as a gas, which is why it's dry. We call it dry ice because there's never any liquid. If you just take a chunk of dry ice and let it sit out, it'll disappear without ever seeing a liquid. Unless it pulls enough moisture from the air. If we're in a humid environment, it'll pull moisture from the air. And then you'll see liquid water, but you won't see liquid CO2. Because it goes straight from solid to a gas, which we call sublimation. Can everything sublime though? We don't see water doing that very often. But it does. Water does sublime, just not at sea level. And not really even at our altitude. But what's the difference between snow and hail? They're both solid water, right? Hail goes from being water as a gas in the upper atmosphere to water as a liquid in the upper atmosphere to water as a solid. Snow goes straight from water as a gas in the upper atmosphere to water as a solid. So snow is a deposition process when snow forms. So the opposite of sublimation is going straight from a solid to a gas. Going from a gas to a solid is called deposition. And actually we do see that at our altitude and even at sea level under the right conditions. If the humidity is just right and the temperature is just right, we can actually get solid or gaseous water vapor to turn solid without getting a liquid phase in between. Which is the difference between frost and rain that then throws on the ground. Rain that falls on the ground is going through this liquid state, but frost never has a liquid state. That's why frost looks different than just my car got rained on and then it froze. Everybody here has seen both of those in everyday life, right? That's why they're different, is because frost forming is deposition. The other thing to remember with these phases is that there's energy associated with them. So even if they're the same temperature, solid water has a lower energy than liquid water. Which is weird, because we talked about energy as temperature as being like the average kinetic energy of the molecules, right? Well, it turns out that wasn't the entire picture. Because when we have a liquid, what makes it liquid is that the molecules can kind of move around each other. When something is solid, they're stuck in that lattice structure, like that carbon we talked about earlier. If they're stuck in that lattice structure, they could still move faster or slower, but they're basically vibrating in place. When it's a liquid, they're actually free to move around. And so they have more energy because they can move further. So the system as a whole has more energy as a gas than it does as a liquid. And it has more energy as a liquid than it does as a solid. And it's the energy associated with the different phases is sometimes called latent heat. Latent heat. Heat means energy changes hands, right? when something's going through a phase change, it actually doesn't change temperature when you're dumping more energy into it. What temperature does water boil at? 100 Celsius. What happens if you're boiling a pot of water on the stove and you turn the temperature on the stove up? Does the water get hotter? Does it stay at 100 Celsius?
Maybe more data.
It stays at the same temperature because all that extra energy we're dumping into it is going towards the phase change, is going towards the water turning from liquid to a gas. So we're dumping more heat in, but it's not changing temperature, which is why they use this term latent heat.
So okay, for sublimation and deposition, is it about the amount of time that it takes for that phase change to occur?
No.
It doesn't settle at the liquid temperature.
Hold that thought for a second. All right, just before we go to the next slide and talk about how we can control which route it takes, I want to just introduce these terms. So the latent heat is the heat associated with a phase change. Every substance has 3 distinct latent heats because there's 3 distinct phase changes that can happen. Right, so heat of fusion is the energy that's required to either melt something or freeze it, the energy that's given off when it freezes. So if you take ice and you add energy into it, it melts, right? If you have liquid water at 0 Celsius and you want it to freeze, you have to take energy away from it. So the other way of thinking about that is when something freezes, it gives away energy to the surroundings. Just like when something hot cools down, it's giving off energy to the surroundings, like our lab. The amount of energy that it gives off when it goes through a phase change is based on what that substance is. So this heat of fusion is the energy required either direction. You either have to put the energy in to get the solid to melt, or if your liquid is freezing, you're going to release that same amount of energy per gram. And vaporization is the same way. When you boil water, you're putting more energy into it to put it into the higher energy state, even if it's at the same temperature. When water condenses, it's going to give away energy to the surroundings. Has anybody ever been to a really humid environment in the summer? What happens when you take a nice cold drink out of the fridge? It gets covered in water. It condenses on the outside of your drink very, very quickly, right? That actually warms your drink up because that water that's condensing is giving away energy to the surroundings. So your drink warms up very, very quickly in a humid environment, unless you cover it. If you don't give it place for the water to condense, the moisture to condense from the atmosphere, it stays cold longer. So if you've ever been to the Midwest in the summer, they love their koozies on their drinks, right? Every single time you grab a can out of the fridge, you immediately put a koozie on. At least with my wife's family in Minnesota. That's not because you're going to keep it colder because your hand is not touching it. That's part of it, that helps. But it's more about you're not letting water condense on the outside of the can. So your drink stays cold longer. I think in a few slides I might have us do a practice problem with that, with real numbers. But it's something like if 10 grams of water condenses on the outside of a can, it'll take your can from being 34 Fahrenheit to 70 Fahrenheit in a very short amount of time. All right, so the other thing to keep in mind is that just like with our specific heat, water has its own specific heat, 4.184 joules per gram degree Celsius. Every substance has its own values for these phase changes too. because water is a polar molecule, the water molecules stick together really tightly. Water has a pretty high value for these phase changes. It takes a lot of energy to go from solid water to liquid water. And it takes a lot of energy to go from liquid water to gas. Other substances evaporate very, very quickly. Anybody ever done any work in a medical office where you had to use alcohol swabs, where you gave an injection or something like that? Or had a shot at any point? The alcohol evaporates really quickly off your skin, right? Because alcohol is not as polar as water. So it has a different latent heat for evaporating. All right. Another random quiz question that perfectly set up the next slide. Do all substances that crystallize increase in volume when they become a solid? Because water does, right? We all have experience with if you put water in a water bottle and then put it in the freezer, it expands. Or if you put a can of something in the freezer, when it freezes, the can can explode. Turns out water is actually pretty unique that way. But we can actually talk about this if we add one more tool, which is what's called a phase diagram. A phase diagram is basically, instead of thinking about phase changes only happening at a set pressure, living up here in the mountains, we know that altitude affects the pressure up here, right? And our pressure being different up here changes how we have to cook or bake. Because the temperatures of phase changes are dependent on pressure. If we're sitting at, see, is this water? This is not water. Here's a phase diagram for water. If we're sitting at 1 atmosphere of pressure, so sea level, when we look at what temperature water will freeze at and what temperature it evaporates at, we're looking at basically one cross section of this graph. We're saying, okay, if I'm at a low temperature at 1 atmosphere pressure, as I move from left to right, I'm increasing the temperature. So I'm starting with ice that's colder than 0 Celsius. As I move to the right, I hit this point where my solid water melts. That's 0 Celsius. If I keep going then, I'm still increasing the temperature. And then I get to a point where now I hit a boundary between liquid water and water vapor. Let me go back to the simplified version here. All of these different phases all show up at different combinations of pressure and temperature. We're used to thinking about water just in the context of at 1 atmosphere or at 0.8 atmospheres in our case at Tahoe. But we can actually dictate what phases exist by changing pressure as well. So what was your question earlier, Torben, about?
I thought that it was related to time, but it's actually pressure.
It's not time, it's actually pressure. If you drop the pressure low enough, you get below this, what they call the triple point. If the pressure is low enough for that substance, you will not see a liquid. So the triple point for carbon dioxide is higher than atmospheric pressure, which is why dry ice goes straight from solid to a gas. The triple point for water is lower than atmospheric pressure. So we're sitting up here when it comes to water. So we can see all 3 phases. Actually, we're more like right here. We're just above the triple point at atmospheric pressure. Right, so what this means is that by changing the pressure, we can change what phase diagram happens. Who watched some Winter Olympics last 2 weeks? Most of us probably saw at least some of them, right? Does anybody know why the speed skaters have different skates than the hockey skaters?
Speed skaters don't need to do as much complicated movement.
Yeah, they don't need to move as much, that's why they don't have, the speed skaters aren't rounded at the end, but they're a lot sharper too. To the point where they actually have to use like blade proof armor underneath their spandex when you're speed skating, if you're doing the short track. Because you can actually get very injured that way. Ice skating works because ice is unique almost in that it has a negative slope here. Ice is most dense as a liquid. It expands when it freezes. But if we're sitting right here, let's say that this is our conditions at the ice rink. We can get that ice to melt by increasing the temperature, and then we hit a phase change and we see liquid ice. What ice skates do though, is without changing the temperature, they increase the pressure. So instead of a horizontal line where we're changing the temperature, we get a vertical line. That vertical line means you can get ice to melt without it warming up. So when you're ice skating, the speed skaters in particular have such narrow blades, it's not just about decreasing drag, although it is partly that, it's also about getting as much of an increase in pressure as possible. Because when you're ice skating, you're not actually sliding on solid ice, you're actually gliding on liquid water on top of the ice. Your skate melts the ice underneath you, and then as soon as you remove the extra pressure, it goes back to being a solid. If you're really careful to not scrape the surface of fresh ice, has anybody ever skated on fresh ice, done much ice skating? If you're really careful on fresh ice, you can not scrape the ice, but you still leave a mark behind you when you skate on it where the water refreezes after you move off of it. Which also means you can get to the point where it's too cold to skate. If we started over here instead and did that same amount of increase in pressure, we're still on solid ice, right? So basically you can get to the point where you can't ice skate. You put on your ice skates, you go out onto the ice, and it's like trying to ice skate on plastic because it's not melting underneath you. So fun fact, when they do those, when the NHL does those outdoor games, they actually have to warm the ice if it's in a really cold environment. I mentioned my in-laws are from Minnesota. They went to a game in Minnesota. There was an outdoor game that it was, I think the high for that day was 10 below. And with wind chill. And they actually, the players were complaining that the ice was too cold. They couldn't keep the ice warm enough for the NHL players to skate on it. So it was a really slow game. Not because it was slushy, but because it was too cold. And as much as my in-laws are diehard hockey fans, they didn't even make it to the third period. I think they left after 2 because you ever tried being outside for an hour straight without moving around in 10 below? It's not particularly pleasant. You can tell the pros though because they come with their heated vests and they bring cardboard. Stand on cardboard so you're not standing on cement, and that helps a lot actually. You'd be surprised at how much standing on a piece of corrugated cardboard helps you not lose your heat. All right. So what's the big takeaway here before we take our break? These phase diagrams always have the same general shape. It's always pressure on the Y, temperature on the X. And at low temperature and high pressure, you're always going to see the solids. Reverse that. At low pressure and high temperature, what are you likely to see? Gases. So And then in between, you see liquids. It's always this sort of Y shape where you hit a triple point where all three phases can exist at the same time if you have the right conditions. And then the other piece here is this critical point. Basically, this line between solid and liquid, it goes up indefinitely. It changes shape a little bit. Sometimes there's more than one type of solid you can form, like with carbon. But the line between liquid and gas basically disappears once you get to a certain pressure and temperature. They call that the critical point. Critical point is basically where you stop being able to tell the difference between a gas and a liquid. They behave interchangeably, and so they call that supercritical fluid. Kind of like a gas, kind of like a solid or a liquid. Basically, it's got enough energy to be a gas, but it doesn't have enough space to be a gas. If you picture taking gas molecules and forcing them into a really, really small container, they still are the same temperature they were before. But now they don't have enough space to stay as a gas. So they behave like something that's kind of in between. So how might this show up on the final? Might say, draw a phase diagram. And then I can say something like, if you started at the triple point and decreased the temperature, what phase is formed? So let me clear this off. If we started at the triple point and we decreased the temperature, what phase are we going to form? It's going to be a solid. If we started at the critical point and we decreased the pressure, so there's the critical point. We started at the critical point and we decreased the pressure. We're making a gas. If we start at the critical point and we decrease the temperature, we get a liquid. So basically, the way that I'm going to ask questions about this is, I haven't decided if I'm going to have you draw it or if I'm going to draw it for you. But it's going to be like, okay, draw an arrow that represents evaporation. Okay, evaporation would be starting as a liquid, going to a gas. Or start at the critical point, decrease the temperature. What phase do you make? And that one's actually kind of a tricky one. If you start at the critical point, you decrease the temperature, you make a liquid first, but then what happens if you keep decreasing the temperature? You get to a solid eventually. All right, so this is a more complete picture of how phase change works. For the most part, us being Earth-centric, as we live on Earth, are mostly as a species, I think something like 90% of all of humanity lives within 100 miles of sea level, or 100 feet of sea level. Take it back. For the most part, we can just look at our cross section here. We don't actually need to think about it this way unless we start getting into different pressures. All right, one last thought, just to fully answer this question. These two phase diagrams show us the difference between water and everything else. Water has this negative slope here, which is why we can ice skate on it. When we increase the pressure on water, it turns into a liquid. That doesn't work with most substances. Most substances have a positive slope here. If there's a positive slope, that means if we started as a liquid and we increase the pressure, we get a solid instead of the other way around. So water is fairly unique in that it has this negative slope, that it's more dense as a liquid than a solid. Most things are more dense as a solid, so they're gonna have a positive slope like this. If you increase the pressure enough on most substances, they turn to a solid. You increase the pressure enough on water, on ice, it turns to water, liquid water. It's so, but because we're water-based organisms on a planet that has lots of water, and water is the substance that we deal with changing phases the most, people tend to think about water as being the normal version. Turns out water is the exception. All right, let's take a break. Let's come back at 11:30 and we'll talk about how we can use those energies.
I didn't see you, I can't lie.
Okay.
Sitting about. What might
What
take.
did it look like? Was it silvery or was it dark? Fire pellets.
Yeah.
Then that was.
Thank you so much.
Yeah.
You can hang on to it in case you need it for another class, but thank you. You feeling better?
Yeah, way better. I think it's a.
Okay,
It's,
as long as you're feeling better.
I think I'm okay, but I'm like, he's like, so I can't clear you until you see the cardiologist, so you know that. They probably won't be able to get me in for like 2 3.
Well, if it's. I don't know what insurance you have. We actually take kids and we go down to Carson.
Yeah,
My wife and I and our kids, just because they have a lot more appointments and a lot more doctors.
no, because it happened like during soccer practice, I get covered on field insurance, cause I had Western Open.
Right.
I am in Blue Cross, but now.
So you have to go to Parkland because it's on school's insurance. So you're dealing with my wife,
Oh, good,
Laura from HR is
yeah,
my wife, yeah. She deals with all the accident insurance and all that stuff, so
she might have called me this morning then,
likely.
maybe. Does your back hurt? Oh, I feel like my back hurts, the hanging, I was like straining my back, but that's cool. I feel like I grew. Like, I know, I got so like stretched out. That was fun. I think I'll do it down. And I was like, I'm good. She's kind of scary too. She's cool. She's cool, but she's a little intimidating. I was not expecting that. No, anything like that. Yeah. I love it too. Oh, chill.
Hey, Sean, for the, description for the example, the ice and the, is this version involve temperature increase?
So-
Or is it not enough?
In general, friction increases with temperature, lower temperature is typically less friction. So like, you've ever seen like, drag racing, they warm their tires beforehand. But really, so that does play a role, but it's a much smaller role because sliding on liquid water is a lot lower friction than sliding. Sliding on ice is still easier than like sliding on wood or sliding on carpet, but it's not as good as being on a like cushion, basically.
I just said waiting for now. Yeah. It's okay, but like then it's really, you know, weird. Like shapes and I check it. I just made it through as all. I think Buddy. No, that's Levy. You guys really think this green? Forever, never gonna see that one Miranda again in my face. No. I didn't even know it was gonna feel like. Oh wait, what's it called? It's about Phoebe. Like leaving for a year and not remembering. And just who was in after. Yeah. National University. And all that stuff, right?
Yeah.
Okay, so when I go to chemistry, what, like, I just like,
No, sorry, there's one in particular that they,
like, I'm trying to give you my money. Yeah, you want money, okay. And they have this,
so if you hit play on that one,
certain apartments, like.
and I think it does, it's towards touchscreen too, so I think you can.
Okay, so when I do that, then I can fill out like a senior hours. Gotcha, okay, I just want to be mistaken.
Yeah, no problem.
Is it like further down the Elm Bay Road? No, actually, instead of turning on Elm Bay Road, it's gonna continue going. Like, that's kind of like, yeah. Nice neighborhood. Are you staying there? Yeah. I was gonna leave, but yeah, I did. What? I'm feeling it's in the middle. No, it's here because feel like not a person. The cover is not it. I guarantee you it is never. I know that Bailey's first year. I don't even think it was this bad. Oh, yeah. Like, I know Bella and Kate and Kelsey. Everyone likes it. Last year, so good. My dad, that's why I was so excited. I was like, oh my God. I wish I didn't. I know. They've given us in the dark. Even though that's the fucking isolation experience. Literally doing despair, bro. Like, you, not by you. Maybe that's I know. I just live in very wait, we were talking about that last time. Yeah. We put fucking class. It was a gym yesterday. Like class, how much that you did. I got a membership there. Yeah, I went to class and it was literally awesome. It's like, what do you see? Yeah, this was. I definitely should not have been doing it. That's looking gross. Yes. Like, you're supposed to bring your core. No. Yeah, no. It definitely did not work. It was not core. That's barely fun. And then we did. Yeah. I did have work. And I was like, oh. Sometimes it's like, you know. So when I was on the bike, I was just like pretending. Right, you could see through the window. I don't want to like that. Think I'll have ass at Martin. Yeah. Yeah. Today I didn't. Wait, what all did you do to this? It was actually so light. It's the late show. Yeah, he's so chill. He doesn't even make you say so. He's like, does he just okay? Let's go. He just gets like motivational tangents. No, just today I was like, we're out here. Well, last time he did that, I was like, oh, like I'm about to have like classes. I go. I thought you just like cut it, and then he kept talking. I was like, oh, I tried. I tried. Never did. You're keeping still. Oh, it's next week. Next week. Yeah, there's a year fix. I don't wanna go shit. You guys. No, because I won't be able to get into the cardiologist. Why? I didn't know. JT's like, yes, you're not gonna burn my little, wait, what? I can't do something, lift like a little. No. We didn't even. I guarantee we didn't do shit today. I don't mind giving up, and then he was like, oh, you weren't practicing Friday. And you're not playing the game. What? We're not being that Slayer. Like, just. We want to win it.
Alright, as everybody's coming back in here at 11:30-ish. Let's try and use this enthalpy of fusion idea.
So we better not come in the bus. I'm gonna be big for service. No, we finished it all. I forgot to rush. I need to drive because I got too busy last Sunday. Road. Who drove you? Jeremy. Oh yeah. Yo, oh yeah, no. One time I was chatting it up with Jeremy. He does it with his stuff. I'm like, he doesn't learn how to use it. I was like, I think he's like. Because the teaching talks about like the kids who like were afraid and confused. They just don't understand, they just want to play all the words.
Alright, so key idea here with these energies. These energies are not in straight joules. They're in joules per gram, or sometimes joules per mole. If they're in joules per gram or joules per mole, they're conversions, right? Just like we saw with density. Remember how we used density as a conversion because it was grams per cubic centimeter? We can do the same thing with energies. Anytime you've got an energy that's in energy per something, that's a conversion. So we actually don't need a whole other Q equation here. We're just gonna use these energies like a conversion. If you've got 15 grams of ice, and every single gram of ice takes 334 joules to melt, we can just set it up 15.0 grams of ice for every 1 gram of ice, 334 joules. Now we're going from ice to a liquid. Are we putting energy into the system? Or is it going to be giving energy away?
Putting energy away. Like, with ice.
If we're trying to get the ice to melt, are we putting energy into the ice or is the ice going to give energy away? We have to put energy into the ice to get it to melt, right? So rather than do that with a positive or negative, the other option is we can actually just put a qualifier on there. The ice has to absorb 334 joules for every gram that melts. So I like doing this because I think in terms of conversion factors, and because I don't like putting negative numbers in conversion factors, that seems wrong. So I always come back to, I'll either put the word absorbed or released when we're doing these sort of calculations. But then we're looking at grams of ice cancels grams of ice, we just left in joules absorbed. We're gonna get something close to 5, just under 5. How much is it, Carmen?
5,010.
5,010. Which we only get to keep 3 sig figs, which means we gotta do it in scientific notation. We should be getting good at that by this point though, right? 5.01 times 10 to the 3 joules. Or it's an even factor of 1,000, right? Which means we can put it in kilojoules pretty easily. Think about the energy from that example at the beginning of class, when we talked about the iron warming up. Iron going from 90 Celsius all the way down to 20 Celsius only gave off at 780 joules. And now we're at 20 grams fire, 25 grams fire, or something like that. This is a little more than half as much ice. And it's absorbing 5 times as much energy. There's a lot of energy in these latent heats. The phase changes, especially for polar compounds like water, these phase changes take a lot of energy. Which is one of the reasons why we put ice in our drinks. It keeps it at melting point of ice until all the ice is gone. And it takes a lot of energy to melt the ice. So, I don't know if any of you have ever worked in a restaurant. When you are filling up a soda cup for somebody, you always fill it almost all the way to the top with ice before you put the soda in it, right? That's not actually about trying to, like, you know, cheat them out of the soda that they paid for or anything like that, because you're gonna go refill it anyway, right? It's really because if you don't put enough ice in it and it melts right away before it can get the soda cold enough, then they're gonna call you back over to the table and you're gonna have to go refill it again and put more ice in. You fill it all the way to the top with ice, it's gonna stay cold as long as there's ice. You don't have to think about it as much. Maybe it's just a pet peeve of mine, but I really hate not having ice in a cup that should have ice in it. So when the ice melts, I always get up and refill, put more ice in my drink because I want it to be at 0 Celsius. All right, we have a number here, 5.01 times 10 to the 3 joules. If we put this in 150 grams of water, so we took 15 grams of ice, one big ice cube, and we put it in 150 grams of water that started at 60 Fahrenheit, what's the temperature after all of the ice melts? So your 60-degree, while your room temperature water should drop, the temperature should drop, right? We want to find, we have something changing temperature now. Which means we're using that equation. We know the specific heat of water. We know the mass of the water. We're trying to find delta T. So what do we plug in for Q? What's changing the temperature of the water? The ice melting. It takes 5,000 joules to melt all the ice, right? That energy had to come from somewhere. It came from the warm water. Right, so this is really just like that question from the lab about you have hot metal and cold water and their temperatures both change, right? Except in this case, the energy is going into melting the ice instead of warming up the cold water. We're cooling down warm water now instead. So we're gonna plug this in for Q. We can say that Q for the warm water equal to negative Q for the ice melting. So if it takes 5,000 joules to melt the ice, the warm water lost 5,000 joules. So Q is equal to negative 5,000. CP is a given, mass of water. 150 grams. Solve for delta T. Something like 6 Celsius. Five thousand over 4 is a little bit more than 1,000 divided by 150. Be some, maybe closer to 7 Celsius. What'd you get?
That's 0.98.
I was treating Fahrenheit Celsius though.
Yeah, so we need to now change, we need to convert our units where we can find our final temperature. And temperature is a little bit tricky that way. But that's a reasonable amount. Right, when you think about, I took a big ice cube and I put it into a glass of water. The ice is gonna melt before the water gets all the way cold if it's just a single ice cube, right? That seems like a reasonable number. So then we just wanna do. We do get to keep all those sig figs, good. So delta T is negative 7.98 degrees Celsius. And our initial temperature. 60.0 degrees Fahrenheit. So we just want to put that Fahrenheit in Celsius before we can find our final temperature. You can't easily convert, I mean, you can, but you have to be really careful. Convert a change in temperature from Celsius to Fahrenheit. It's a lot simpler to take your Fahrenheit temperature and convert it to Celsius, because a change in temperature is different than just converting regular temperatures. So I'm gonna recommend you never try to convert a change in temperature to different units. Because it's easy to confuse yourself. It's always easier to convert this. If we could say Fahrenheit is equal to 1.8 Celsius plus 32. So 60.0 equals 1.8 temperature in Celsius plus 32. The temperature in Celsius is 28.0 over 1.8. Do the subtraction first, then divide by 1.8. Get something like 18. 15.5. So subtract 32 from both sides. And that gets 60 minus 32 is 28. And then we're gonna divide both sides by 1.8. So our initial temperature in Celsius is 15.5. So what's our final temperature then? Where delta T is equal to final minus initial. We solved for delta T already. And we just converted our initial temperature into Celsius so we can plug it in. Negative 7.98 equals TF minus 15.5. So TF is going to be 7.5 after we 7.52, except because this is addition and subtraction, we're keeping the same number of decimal points as our least number of decimal points, so we can only go to the 10th place. So we just get 7.5. It's really all just units and conversions. Depending on how you felt about the first week, the first month of this class might not be reassuring. We're gonna keep coming back to units and conversions because almost everything in science at this level is about units and conversions. At least the mathematics are, all just units and conversions. All right. Let's look at one of those cross sections of the phase diagram. This is what's called a heating curve or a cooling curve. I've heard it called a heating curve or a cooling curve, regardless of whether you're starting hot and getting colder or the other way around. So they use the terms interchangeably. As shown here, it's a cooling curve. What we're really looking at here is we're looking at the temperature of a bunch of water as we take energy away from it. As we remove energy from this water, initially we're starting at 140 Celsius. So we're starting at steam, gaseous water. As we take energy away from it, the temperature drops until what? What's happening? We're taking energy away, but the temperature is not changing. What's going on there? It's phase change, it's condensing. Anytime you see a flat spot on one of these heating or cooling curves, it's a phase change. Right, so on our phase diagram, remember, if we're saying this is 1 atmosphere pressure, we're basically starting over here, dropping the temperature, and ending at minus, call it minus 25. When we started at 140 Celsius. Right, so this is what I mean by this heating curve is a cross section. We're just taking one specific pressure of this phase diagram. We're starting at a certain temperature, we're dropping the temperature. And every time we hit one of these lines, we get a phase change.
This is the average temperature of the system, I assume, because wouldn't the water still be decreasing in temperature and the steam transitioning?
It turns out that energy is what's called a state function, which means all that really matters is where you start and where you end. The actual path to get between points A and B doesn't matter. So even though, yes, some of our water is going to be not staying at 100 Celsius, the whole system, if we're trying to get the total amount of energy for these change, we treat it like it's gonna all stay. And if it's well mixed, it will all stay at the same temperature. The only time you get a temperature gradient where you get a difference in temperature is when it's not well mixed. And so we do a lab. It's in Gen Chem, it's it's a really boring lab, but the data looks really good. If you like data analysis and spreadsheets, it's actually great. Getting the data is really boring because you literally just start with a beaker full of ice and you put it on a hot plate. And you measure the temperature every 30 seconds until it's boiling. So you're literally watching water boil. But we get good numbers for it, and we get a heating curve then, where if we're looking at time versus temperature in Celsius, we get something where we start at, say, -5, temperature increases until it gets to the melting point. And then the temperature flattens out until all the ice is gone. And then it starts going up again until you get to 100 Celsius. And then it flattens out again. So really, realistically, with real world numbers, basically all that happens is, as long as it's well mixed, we just get sort of like a little bit of a rounding on these corners. But for the most part, it's a pretty good assumption, and the math still holds up, where we can just say, if we really just want the total amount of energy, it doesn't really matter if that's rounded or not, we're still just trying to find sum of all of these processes put together. Alright, so why are these cooling curves or heating curves all that useful? Because it allows us to break up what's happening into distinct steps that we know how to do the math for. If we want to get the total amount of energy that it takes to go, that's going to be given off from 100 or steam at 140 Celsius all the way to ice at -25 Celsius, we can figure out exactly how much energy, not exactly, within sig figs, how much energy that's going to take, because all of these individual pieces we know how to do the math for. Anything that's got a slope, anything where it's not flat, we know how to do that. Anything that's flat has one of those delta H values, those enthalpies, those latent heats, which means we know how to get that energy too. So what's useful about these is it allows us to break up the total process into distinct steps that we know how to do the math for. So it allows us to answer questions like, a piece of ice starts at -23 Celsius. How much energy does it take to bring it up to water at room temperature? And so let's think about this. I'm going to put all three parts on the board, and then so our final question, the overall question, before I break it up into pieces for you, is how much energy does it take to change the temperature of ice at -23 Celsius to water at room temperature at 21 Celsius? If we wanted to plan this out, we do a heating curve. We can say x-axis is Q. How much energy are we putting in? And temperature is on the y-axis. So we're starting at -23 Celsius. doesn't have to be to scale or anything like that, we're just gonna pick a point at the bottom and say it's minus 23 Celsius. And we're gonna add energy. If we start with ice at negative 23 Celsius and we dump energy into it, the ice warms up. Until what? What happens if you warm up ice? It melts. What temperature does it melt at?
2 degrees Celsius.
0 degrees Celsius. So then we're still dumping energy in, but the temperature is not changing because the ice is melting. It'll stay at 0 Celsius within sig figs until all the ice is gone. And then we're still dumping energy in. If all the ice is gone and it's turned into liquid water at 0 Celsius, what happens if we keep adding energy? Temperature starts going up. Until I picked an arbitrary endpoint of room temperature. So there's three things happening here. If we took a piece of ice out of the freezer and just set it on in a glass at room temperature, over time, this is what's gonna happen. It's gonna start by the ice warms up. Then it's gonna get to the point where the ice melts. Then it's gonna get to the point where the water warms up. Liquid water. We can calculate the energy for all three of those steps. So, step one. Don't try to do too much at once. I know I just drew this heating curve. And it seems like there's a lot to do. There's some math to do. But the first step is just how much energy does it take to change the temperature of 25 grams of ice from minus 23 to 0? Temperature is changing, so what equation do we use? We know how to use this equation. We've got a mass for the ice. We've got delta T for the ice. We're going from minus 23 to 0. So we need the temperature to increase 23 degrees, right? So delta T equals 23 Celsius. Mass is 25.0 grams. You want to be a little bit careful with the specific heat. I know we use the specific heat of water a lot. But that's specifically talking about liquid water. Ice has a different specific heat, which is given to you. It's actually easier to warm up ice than it is to warm up water. Another case of water being weird.
Then maybe there's something that uses water.
It could have to do with the density, but because this number has to do with grams, and the grams doesn't really change, just the volume does. It's more to do with the fact that there's more energy in those water-water interactions when it's a liquid, because they're moving around more. I'm going to call this Q1, so this is our first step. $25 times 2.11 is pretty close to 50 times 20, get something around 1,000. And how many sig figs do we get to keep? Just 2. So I also converted it to kilojoules, so I don't have to write it in scientific notation. But 1200 joules is 1.2 kilojoules. Step one wasn't so bad, right? Anytime you get a big problem and you don't know what to do, break it up into pieces that you do know how to do. It's the old saying about how do you eat an elephant? Have you ever heard that? It's just something I grew up with. How do you eat an elephant? One bite at a time. Doesn't matter how big the problem is, as long as you know how to do every step individually. And at the end, we're just gonna add them up. How much energy is it gonna take to melt the 25 grams of ice? Again, I have to give you the heat of fusion for this. But if you know this number, it's joules per gram, right? So 25 grams, change color for Q2. And every 1 gram of ice is 334 joules absorbed. Or if we're keeping 3 sig figs, so again, just making the point that these phase changes have a lot of energy in them. It took 1.2 kilojoules to go from 23 degrees below zero to the melting point. And it took 8 kilojoules of energy just to melt the ice. So it took 6 times as much energy to melt the ice as it did to warm it up. How do we do Q3? What's happening for this last step? We warmed the ice up to 0 for Q1. We melted the ice for Q2. For Q3, we have liquid water now, and we're warming liquid water up until room temperature. So if the temperature is changing, we're using our Q equation again. The mass didn't change. It's still 25.0 grams. Specific heat did change this time. Now we're dealing with liquid water. And what's delta T? 21. We started at 0 and we're ending at 21 degrees. If we were taking this all the way to boiling, we'd be going from 0 to 100, so then delta T would be 100.
77.7.
In kilojoules, that gives us 2.2, right? But again, I'm gonna make the same point one more time. taking a piece of ice out of the freezer, letting it warm up to room temperature. Almost all of the energy that it needs is in the phase change. Taking ice from -23 to 0 was only 1.2 kilojoules. Going from water at 0 Celsius to water at 21 Celsius only took 2.2 kilojoules. And it took 8 kilojoules to actually do the phase change. So again, this is why ice is such a good way to cool our drinks down, right? Because we go from room temperature liquid, we put some ice in it, it brings down the temperature of the ice a lot faster than the ice melts. So it brings down the temperature of the liquid a lot faster than the ice melts. Alright, so I believe that this is at least half of your quiz this weekend. It's doing one just like this, except it'll be, I'm gonna change it so it's not water, and I'm gonna change the temperatures. But I still have to give you the CP numbers, and I still have to give you the heat of fusion. So it's about planning it out, breaking it up into steps you know how to do. Here's another way I can do it. If I give you the heating curves and ask you to match it to the system I described. At Tahoe, water boils around 94 Celsius because we're at lower atmospheric pressure. If you start with a sample of ice at 0 Celsius and you heat it until it becomes steam at 94 Celsius, which phase or which heating curve matches that system?
C,
How'd you get there?
because we start at 0, so it's not D where it starts below. And then since we're just measuring until it becomes steam at 94 degrees Celsius, we're not measuring beyond that point like it'd be. So it would be C.
So we're starting at 0 and we're ending at 94. And we're starting with the phase change and ending with the phase change. If I said we started with liquid water at 0 Celsius, we wouldn't start with a phase change here, right? It would look something more like this. So just with these heating curves, they're describing a real process. And this is a process that whether you realize it or not, or despite the fact you don't necessarily have to think in graphs, it's describing a process that everybody knows. Water melts, heats up, boils. We all have some experience with that. All that's different about any of these heating curves is where are you starting and ending. A little bit, I threw in a little bit of a curveball by making it go to 94 Celsius instead of 100 Celsius, but if we were at sea level, we'd be finishing at steam at 100 Celsius instead. When we first got married, my wife and I got a rice cooker on our wedding registry. It's just one of the cheap ones. You put rice in, you add some water to it, you turn it on until the light turns green. It boils over every single time because since we've been married, we've always lived at altitude. And those rice cookers are based around the idea that water boils at 100 Celsius. So if you've ever tried to use if you use a pressure cooker, an Instapot or something like that, then those work just fine because it's a closed system. You'll actually get up to the right pressure. But if you use a rice cooker that is one of those ones where you just put the lid on top and push a button and let it go, they almost always boil over up here because it's trying to heat it to 100 Celsius, but the water is boiling at 94 Celsius. It never gets to 100 Celsius until the rice is burning on the bottom. Always made a huge mess. Now we just use a pot like a normal person, but it took me a while to figure that out, even with a chemistry degree. All right. Let's be done. Let's be done for the day. I'll see half of you for lab in a little bit. Couple of you tomorrow. Everybody else, watch for the quiz this weekend on energy and phase change.
I think that is